Ah, the order of operations. Whether you know it as PEMDAS, or GEMDAS, or PEMDAS, or some other acronym, it probably, unfortunately, brings back many not so fond memories of naked computations like this. And that's unfortunate because math is way more than just computation. And it turns out the order of operations is surrounded by myths. And many of these myths have led to some of the negative attention given to mathematics in general and the order of operations more specifically on social media recently. And we'll come back to this in a little bit. But first, I want to tackle some of the myths that are out there about the order of operations. So let's get started. The first is that the order of operations is a convention that was decided by mathematicians a long time ago. I'm not sure where this myth got started, but as it turns out, the debate about what the order of operations should be is actually less than 100 years old. And in terms of mathematics, which has been around for thousands of years, that's really not that long ago. And incidentally, the debate about the order of operations actually coincides with the beginning of the use of textbooks in the early 1900s. So that's kind of interesting that we didn't really see a need for an order of operations prior to textbook use. Something to think about. The second part of this myth is that the order of operations is a convention. So, conventions are ways to represent something that could easily have been decided on differently. For example, on a number line, the positive integers are on the right side, but this could have been decided differently with no consequence to teaching or learning mathematics. And this is how conventions in mathematics work. The order of operations actually does have a mathematical basis. To show you what I'm talking about, take a look at the expression below to see why multiplication precedes addition. So 6 plus 3 times 5, because multiplication can be defined with equal groups, we can interpret this expression as 6 plus 3 groups of 5, which might actually look like this visually. And it can be rewritten as 6 plus 5 plus 5 plus 5. Now, because of the commutative property, these numbers could be added in any order, maybe from left to right. 6 plus 5 gets 11, plus 5 plus 5, 11 plus 5 is 16, plus 5 equals 21. Or maybe we could add a different way. 5 plus 5 is 10, 6 plus 5 is 11, 11 plus 10 is 21. To me, that way seems a little bit more efficient, but either way, the equivalence of the expression remains intact. But let's take a look at what happens if we add first. By adding 6 plus 3, we're changing the meaning of the expression to 6 plus 3, or 9 groups of 5. Visually, at the bottom of the screen, you can see what that looks like and how it differs from what we saw in the previous screen. Either way, this is not equivalent to 6 plus 3 times 5, nor 6 plus 5 plus 5 plus 5. So rather than dismiss the order of operations as a convention, why not engage students in exploring equivalence to determine why the operations are ordered the way they are, and what role the context of a problem plays in determining how to write expressions? Myth number 2. The order of operations is a strict set of rules. So teaching the order of operations as a strict set of rules is mathematically confusing, since the properties of operations tell us that we can, at least sometimes, rearrange numbers using the commutative properties of multiplication and addition, We can sometimes group numbers differently using the associative properties of multiplication and addition. And we can even alter the order in which operations are performed using the distributive property of multiplication over addition. So 7 times 12 is the same as 7 times the quantity 10 plus 2, which is the same as 7 times 10 plus 7 times 2, which makes 70 plus 14, which is 84. So let's take a look at an example. So following the order of operations, first we do 2 to the third power equals 8, then multiply 3 times 14, which equals 42, then 16 times 3 equals 48, and finally we add them all from left to right. 8 plus 42 plus 48 equals 98. But there are really many other ways to evaluate this expression. First, any of the parts that are added can be done in any order. So looking at this as an addition problem, I can multiply 16 times 3, and then I can do 2 to the third power, and then I can do 3 times 14, and then all I have to do is add those up in any way I want. I don't have to do 2 to the third power first, just because the order of operations says to do exponents before any other multiplication. Also, if you realize that both the 14 and the 16 are being multiplied by 3, you can multiply 3 times 30 instead. 30 is the same as 14 plus 16, and they're both being multiplied by 3, so why not do that? This makes the problem 8 plus 90, which equals 98. Maybe a little bit more efficient way to think about this problem. As a result of teaching the order of operations in an only PEMDAS is allowable kind of way, students miss out on opportunities to look for equivalent approaches that help them develop fluency. Mathematically proficient students look at the whole problem, consider what they know about the properties of operations, and determine how they should most efficiently find the solution. They take the opportunity to look at the structure of the expression, how numbers are arranged, and any number relationships to determine efficient solution paths. Myth number 3. The order of operations is accepted universally. Well, this one is a little bit math and a little bit myth. The basic order is common across all countries, but there are some differences in how they're described. In some countries, for example, they explain that division has to be done before multiplication. In the example below, 40 times 30 divided by 5. As we do it in the United States, the operations would be completed from left to right. 40 times 30 is 1200. 1200 divided by 5 gives you 240. In some other countries, students are told to divide first. So it would look like this. So 40 times 30 divided by 5, they divide 30 divided by 5 to get 6. And 40 times 6 would give them 240. It's the same thing. So it turns out that multiply and divide in order from left to right and divide before you multiply both describe the same steps in the order of operations. If you're not sure if you believe me, choose some other numbers to play around with, see what you can figure out. I'd like you to notice, though, that 40 times 30 divided by 5 can be rewritten as 40 times 30 times 1/5. Now, since the expression on the right of this equation is all multiplication, that allows us to use the commutative and associative properties, which kind of proves why both of these rules are equivalent. So let's come back to this social media storm that was happening and actually continues to happen regarding the order of operations. Not long ago, People argued for weeks across multiple social media platforms about what the correct answer was to each of these computations. And there may have been other problems that were similar to this. And normally, if something gets people talking about mathematics, I'm all for it, all in. This, however, really started to involve a lot of trash talk, which has become too much of a norm in our society. And I think it's due to social media, unfortunately. And that's neither productive nor nice. So I kind of stepped away from it all. And the reason for this explosion of trash talk stems from a belief in some of the myths about the order of operations that I shared previously. In addition, with these specific problems, there is an obvious lack of context and or communication regarding what the person who wrote the expression wanted you to do. These expressions are written to be vague. I'm not sure why they were written to be vague. My guess is to incite a disagreement and possibly an unproductive discourse. I'm just guessing. But you see, we have a reason to write expressions and equations and create graphs and record our solutions to problems we solve. And that reason is to communicate our mathematical thinking to other people. Ultimately, as humans who use mathematics, the goal of writing expressions like this is to communicate mathematical meaning to an audience just as authors communicate their ideas. Precision and clarity is key and really can come in many different forms. So let's take a look at this expression. Whoever wrote this expression could have added a context to convey his or her meaning about what this expression was about. Here's a context that I came up with. 6 cookies are shared with 2 groups, and each of those groups have 1 boy and 2 girls in it. How many cookies does each person get? Well, this context communicates that we're doing long division as sharing. I'm sharing 6 cookies with 2 groups of people, each of which has 1 boy and 2 girls. In order to solve this correctly, I have to find out how many people there are. And I know in this expression that all the people are on the right side of the division symbol. So I have to do that first. Then I can divide the 6 cookies by all people. If this person who wrote this wanted to communicate to do the division first, so 6 divided by 2, this person could have added grouping symbols. Or they could have written 6 divided by 2 as a fraction. Either way, even without a context, these 2 equivalent expressions are much clearer. So as you become a mathematical author, as you work on telling your mathematical story, as the author of all of the problems that you solve that are worth solving, stay aware of your audience, who you're communicating to, and what mathematical message you're trying to convey. Using context or just being more precise with your written mathematical language allows for better communication and clearer understanding for everyone. And remember, and stay away from the myths. Mathematics makes sense. Use your sense-making abilities as you're solving problems. Anything you do in mathematics must make sense. And if everyone does that, maybe it'll cut down on some of that math trash talk on social media. One can only hope.